Before getting to the session, I have a little announcement about the international conference on heavy electrons and noble phases, a satellite conference of ICSM 2012. It's going to be held in Gwangju, South Korea from July 5th to July 7th. And you can see the topics: noble electronic phase, heavy electron systems, conductivity, and you can find the plenary speakers, Jack Floke, Frank Stegwitz, Thomas Timusek, and all other good people. So if you are interested, please take a look or just type ICSM 2012. Okay. Okay, so my name is Tuson Park, and from Sungkyunkwan University, and a chair of the first morning session. The first speaker for this session is Dr. Daniel Braithwaite, and he's going to talk about PTH phase diagrams of Fermion systems. Right.
Thank you. So good morning, everybody. So let me first thank the organizers for giving me this opportunity to present this work. The original title was somewhat vast, so as you see, I've narrowed it down a bit. I want to first thank also my collaborators. So inside the CEA, most of this work was the work of two PhD students, Esther Collier and Amalia Fernandez Padilla, who will finish this year. Many of the samples were grown by Gérald Aperto, and of course Jacques Fluquet is the creator of the Heavy Fermion group and still a mentor. I want to also thank collaborators from outside the CEA, Vicky for the synchrotron work and for high field measurements. Yes. Okay. So for those of you who don't know Grenoble, our situation is quite unique because Grenoble is a good place to come for the mountains, but also maybe I should change sides. But also for science. You see our situation here in the CEA. We're surrounded. Our nearest neighbours are CNRS, particularly with high magnetic field facilities, ILL for neutron scattering, and European synchrotron. And the possibility to use all these facilities greatly helps our work. Another specificity of the group is that in addition to these physical studies, we've always had a strong effort in instrumentation, and this is particularly true in the field of high pressure, where in the lab it's more than 20 years of development with many, many people involved, which enables us to do what we do today, which is to use the diamond angle cell to reach very high pressures in good hydrostatic conditions, but above all to be able to introduce wires into the sample chamber so we can make, for example, resistivity measurements, but also by putting a thermocouple on the sample, specific heat measurements, or by introducing a tiny coil into the sample space, AC susceptibility measurements. And you see the specificity of the diamond cell is the tiny dimensions of the sample chamber and so of your sample. Another important aspect has been the possibility to actually change the pressure at low temperature. This is the work mainly of Bernard Sals, who's developed a very effective technique using a helium bellow and a lever system to be able to change the pressure in the diamond cell at low temperature. Now Bernard set this up on a very simple helium-4 bath cryostat, which has produced an enormous amount of results on phase diagrams in many systems. We've always wanted to go a step further, and for the past few months we now have working a similar system on a dilution fridge. So we can do the same thing at very low temperature and also put the magnetic field. Of course, if you change the pressure, you have to be able to measure the pressure. This is done with an optical fiber and the Ruby fluorescence technique. So as you put pressure in your helium value, you can actually see the Ruby peak moving and tune and get to the pressure you want in the pressure set. Now, before I come to the main topic, I just want to give a quick example, two other examples of work in the lab. One example is the interaction between anti-ferromagnetism and superconductivity in series systems, and this is the work of Georg Campbell. You can see here that this already rich phase diagram becomes even more interesting when you can add, in addition to pressure and temperature, you can change magnetic field. And some of the most exciting results recently have been on the coexistence of ferromagnetism and superconductivity in uranium systems, which is the work of Dale. So many of you know this work. Now, to come to the main topic, why do we want to study ytterbium? Ytterbium is interesting because in many ways it's similar to cerium. Both ytterbium and cerium can fluctuate between a non-magnetic state, which is the completely empty 4F shell for cerium, and completely full 4F14 shell for ytterbium, and a magnetic trivalent state, which corresponds to 1 4F electron for cerium, and 13 4F electrons, or so 1 4F hole for ytterbium. So ytterbium is often called the hole analog of cerium. Now, in both cases, if we put pressure on these systems, we're going to tend to delocalize the 4F electrons. So this is going to have opposite effects. In cerium, we're going to tend to move towards the non-magnetic configuration, whereas in ytterbium, we're going to favor the magnetic configuration. But this means that in both cases, we can imagine to reach and study magnetic instability by applying pressure. Now, if we want to look in detail what's happening to magnetic instability, the usual approach is the Doniec field diagram. Doniec pointed out that the ground state of the system is going to depend on the competition between two different effects. One is the Kondo effect, which by screening of the local moments by the conduction electrons is going to reduce magnetism. The other is the well-known RKKY interaction, which is going to tend to promote a magnetic ground state. Now, both these effects depend on the same parameter, which is basically the interaction between the 4F electrons and the conduction electrons, but they don't depend quite in the same way. And what Doniec pointed out is that for small j, the RKKY interaction is going to dominate, so you have magnetic order, whereas as you increase j, at some point the Kondo temperature is going to, the Kondo effect is going to dominate, and you will have a non-magnetic ground state. And in between, you have a critical value of j, where you can expect critical point. There's instability or critical point. Now you see that, strangely, it seems I'm now talking a different language to the original picture, because I'm not talking about valence changes anymore. In fact, if you read the original Doniec paper, he says very specifically that non-integer valence states are not taken into account. Now, this is obviously not true in heavy Fermion systems, where these non-integer states are the basis for all the exotic properties. So how can we use this approach to describe what's happening in heavy Fermion systems, and particularly in ytterbium? The reason is that J here is basically the width of the 4F level divided by the distance of the 4F level from the Fermi energy. Now, what's happening in cerium is that if you take a not quite trivalent cerium, your 4F level, the energy of the 4F electron is going to be below the Fermi energy, and by applying pressure, this is going to move towards the Fermi energy, so this term decreases, and J will increase. In ytterbium, the 4F level we're talking about now is the 4F hole, which is above the Fermi energy. So applying pressure, this is going to move away, this term will increase, and J can decrease. Now you see, for cerium, the relation between pressure and J is obvious, because delta, the width of the level, will also increase with pressure. So this term increases, this one decreases, J will increase with pressure. In ytterbium, delta will probably also increase. So you see there might be a competition between the two terms relation. So we can normally expect that J will decrease with pressure, but we can wonder what will happen if, now what I didn't say is that the energy of the 4F electron is obviously closely linked to the valence. So now we re-establish the link between the two pictures. We can wonder what will happen if the valence reaches a state where it no longer changes the pressure. If, for example, we reach a completely trivalent ytterbium 3+, probably epsilon F will continue to vary with pressure, but much more slowly. And so you can imagine that the effective pressure would become much weaker. And in an extreme case, it could even be the increase of delta which dominates, and J could actually start to increase again with pressure. So much for the theory. Now what happens in real life? Can we find? Yes?
So delta is the width of
delta is basically the width of the 4F band. Can we find an ytterbium system which behaves as we expect? Yes? Okay. So ytterbium copper 2 silicon seems to be the ideal system to study. Has a common tetragonal structure. It is an intermediate valence, but not too far from the ytterbium 3+. a moderate heavy fermion. It has good breeding because it's obviously related to the very famous series copper 2 silicon 2. And importantly, we have today very good crystals. And it seems to behave as we expect. More than 10 years ago, it was shown in the resistivity that under pressure, quite high pressure, about 8 GPa, a clear anomaly appears, which was assigned to magnetic order, correctly assigned to magnetic order. And since then, we have confirmed the phase diagram using many techniques, including specific heat and susceptibility. I say it behaves as we expect because you see that in the resistivity there is also a maximum, and this is some indication of what the conduit temperature is doing, and the temperature where this maximum appears decreases with pressure, so we can think that the conduit temperature is decreasing. If you look at the resistivity, you find fermi-liquid behavior at very low temperature, and the temperature where fermi-liquid behavior is present goes towards zero, goes to the critical pressure. And in this region here, we get non-fermi-liquid behavior with explosions which are smaller than 2. So basically, it's at least qualitatively obeying what we expect for quantum critical points from spin fluctuation theory. Now, from the introduction, you can guess that what I'd like to know is what is the valence doing across this phase diagram, and this we've been able to measure recently using resonant inelastic X-ray absorption at ESRF under pressure and at low temperature. And what we see is that the valence increases with pressure, going towards the Fermion 3 plus state, and there is a pronounced kink which occurs close to the critical pressure, and this kink is actually more pronounced at low temperature. But the valence continues to increase, so magnetic order actually sets in before we reach the Fermion 3 plus state, and the valence is increasing basically across the whole phase diagram we measured, which justifies, if you like, that Fermion copper 2 seems to be following the Doniec picture. So Fermion copper 2 silicon 2 appears to be a well-behaved system, except for a few points. The first surprise was that when we measured susceptibility, we found that the magnetic order was actually fermionic. All the techniques which had been used previously couldn't distinguish between ferromagnetic and antiferromagnetic order, and because the magnetic order only sets in at very high pressure, this is quite difficult. So this is one case where susceptibility is very useful. You can see also that if we apply a small field, the ordering temperature increases, and we can even induce magnetic order at a pressure where at zero field none was seen. This prompted us to look at higher fields to see if we could see some sign of metamagnetic behavior. We went to see our colleagues in the high field lab and measured up to 28 Tesla under pressure and up to 60 Tesla at ambient pressure with pulse field. What we see is that under pressure we get a strong magnetic contribution to the resistivity, which is quickly suppressed with magnetic fields, but no clear sign of metamagnetic transition. So the first surprise is that it's ferromagnetic. This actually may be a quite general trend in Fermion systems. There are several examples of systems where ferromagnetic order or ferromagnetic fluctuations are known or suspected, and there's even some kind of explanation given by Watanabe and Miyake for this. Second surprise is that if you see, you might wonder after showing you nice pictures of our dilution fridge, I don't put any points in this region here. The reason is we've looked and we've never actually been able to detect a transition below about 1.5 Kelvin. So it seems that magnetic order appears suddenly at this temperature, and it could very well be a first order transition, which would also be compatible with the ferromagnetic state. We've also, of course, looked closely to see if we could find signs of superconductivity here. We didn't find any. In a cerium system with such pure crystals, superconductivity at a critical point seems to be the rule rather than the exception. In ytterbium, it's very rare because there's only one case possibly known. Of course, the two previous points, ferromagnetism and first order transition, could also be strongly against superconductivity. And finally, we can wonder what happens at higher pressure. You see here the phase diagram, so this part here is taken from resistivity data of Winkelmann and L. This becomes very flat, completely flat. In fact, there's no change. And we're approaching the region where ytterbium 3+ reaches its trivalent state. The valence is changing very little. Very little. In the early paper by the Jacquard group, this maximum is also shown actually to start to increase again at high pressure. So we can wonder if we could measure to high pressure, which is very difficult because the pressure is low, what would happen? Maybe ytterbium copper 2 would become less overheated at high pressure. Now I turn to another system which we thought would be a very good candidate. Ytterbium aluminum 3. It's a simple system because it's cubic. It's also intermediate valent, not very different to ytterbium copper 2 silicon 2. And so we put this system under pressure, and the surprise was that very little happened actually. You can see here the difference between resistivity curves at 1 GPa and 21 GPa. There's very little change. It seems to be going in the right direction. If we subtract the phonon contribution, we see here a maximum appearing in the magnetic resistivity. So it seems that the conduit temperature is decreasing, but clearly we're still a long way from critical points. If we want to know, we haven't measured the variance ourselves, but there is measurement that exists, unfortunately only at room temperature. We see here that the variance is increasing with pressure. Maybe at the pressures we're measuring, we're still around 2.85, so probably this is just not increasing fast enough. So ytterbium 3 basically is going in the right direction, but not fast enough for us. Now, I said in the beginning that it's possible that there could be cases where ytterbium would behave in a completely different way to what we expect. Are there examples of systems which don't follow what we expect? I know at least two. One is the ytterbium 2 palladium 2 tin, where a dome-like shaped phase diagram of magnetism was reported. And last year I was very interested in a poster I saw in SGES, where it was reported that in ytterbium nickel-3 aluminium 9, which is antiferromagnetic at ambient pressure, the ordering temperature was reported to decrease. So we wanted to check this, so we grew single crystals of this material. In this system, the magnetic order appears very clearly as a sharp transition in the specific heat. So it's a good candidate for measuring the phase diagram using specific heat, which we've done. So you see here that this transition. And if we follow the ordering temperature, we see that this indeed decreases with pressure. If we take the first point, if we extrapolated a linear fit, we thought we might be able to reach and study a critical point at a bit above 10 GPa, maybe even lower, because you don't expect really from critical behavior a linear, but something decreasing stronger. Because if you look closely at the specific heat data I showed at the beginning, you guess already it's not the case. This is what actually happens. The ordering temperature starts to saturate, and at higher pressure changes very little. Possibly even though it's within the experimental limit, it starts to increase again at the very high pressures. But so it means that in this system we can forget about looking for a critical point, at least in this pressure region. So here, of course, we'd like to know several things. What is the ytterbium valence doing? We're already very close, or possibly at ytterbium 3+ at the beginning, it seems. What is the conduit temperature doing? What is the nature of magnetic order? There's some suggestion that it could be a change to ferromagnetic order under pressure. So I don't have the answers to these questions today, but these are all good targets for the future. And that brings me to my conclusions, a bit ahead of time. I hope I convince you of the crucial role of instrumentation for measuring these phase diagrams, and the importance of comparing the microscopic phase diagram with the microscopic measurement of the ytterbium valence. And that although ytterbium does behave very often as we expect, and it's a very good tool to compare what's happening in ytterbium and deuterium systems to understand better the phase diagrams of these systems, there are some strong differences. Thank you very much.
terbium compared to silicon 2. So first, the valence chain shows a kink around 10 GPa.
Yes.
Do you have any idea what is the nature of the source of this phenomenon?
So I don't know. Where is the chicken and where is the egg? But it's obviously it's. It's obviously where magnetic order occurs, even though we couldn't measure the valence at the temperature area. We're not in magnetic state here. In fact, we have another curve which is at 7 Kelvin, but we reduce to high pressure, so I didn't show it. But we're not in a magnetic state. We're not far from it. So whether the valence increases and then becomes magnetic and this somehow slows down, or whether naturally this is what the valence is doing and this is naturally where it becomes magnetic, I don't know. I still have some trouble imagining a magnetic order in a non-completely trivalent diagonal state. We can't, of course, discount that somehow as you go into magnetic order, if we could measure, we would jump to completely diagonal 3 plus. But I don't know if I answered your question already, but that's the situation.
The second question concerns the first order character of the phase transition close to the supposed quantum critical point. So your finding would be would confirm the theoretical prediction by Bellis and Kilpatrick that in a ferromagnetic system, stoichiometric ferromagnetic system, no such a situation should happen.
Yes.
And my question is, if you apply magnetic field, do you observe wings of second order lines?
Not yet, no. This is we trouble is these wings. We imagine they must be there, but first, before we can find the wings, we would have to find the change between the first order and second order transition on the phase diagram, and even this is not so trivial. If you look in the cases where it's been measured, you have to look, for example, at features in the Hall effect, something like this. And this, in principle, we could do, but you have to start. Everything starts at 8 GPa, so it's not so easy. But of course, it's when that was one of the first things we thought of when we confirmed this first order transition. We thought let's look for the wings, but before you find the wings, you have to find the body.
Thank you.
Okay. Yeah. It's a general question, not very specific to this. So other examples in the heavy fermions where superconductivity coexists with magnetism with a large local moment? Or are these small, typically close to the critical point?
Yeah. And so the debate of the real coexistence or not is still quite open when you have macroscopic coexistence, but at least macroscopically you have there are several examples, including uranium-germanium-2, where you actually have magnetism ferromagnetic moments.
Right, but microscopically it's not known whether it's a homogeneous state, and are the moments large there, for example,
You have one Bohr magneton, yes.
One Bohr magneton.
Okay, so another question. Okay, then I have a question. So you in similar question what Darius did, ytterbium copper to silicon.
Yes.
So the critical pressure is around 6 GPa or 7 GPa. So what are the normal state right above there? Do you see any anomaly above, say, around 6 GPa as a function of temperature?
In what, sorry?
In resistivity or even the specific heat management or any
So,
management?
yes, if we look, for example, at resistivity, in this region we have a thermodynamic behavior.
Right.
If you follow the T-square coefficient, this is increasing very, very strongly, about two orders of magnitude, increase between zero pressure and critical pressure. Then, what you would expect normally in magnetic state is a decrease again.
Right.
This it doesn't do. It continues to increase slowly. This is a strange behavior. This may be linked to the first order state. The most power Fermion over several GPa above the critical pressure. It may be linked to the fact that the valence is still increasing. I don't know. But we do see anomalies, of course, in the specific heat is also, with our calorimetry measurement